Good morning, everyone. I hope you can all hear me okay. In recent times, full waveform inversion has shown a lot of promise in helping us obtain a high-resolution model, a high-resolution image of the subsurface. And with increase in computing power and a better understanding of the problem, we've been able to incorporate more factors into our inverse problem. So it's becoming sort of routine now to perform FWI for VTI media. But it's almost always done in the acoustic approximation. So here we are attempting to perform FWI for elastic VTI media. We are constrained to 2D models now, and since diving waves are the first kind of the first data that are inverted, we are going to just look at transmission data here, and then we'll move on to reflections later on. So, as I said, for waves that are polarized in the plane of propagation, we need 4 model parameters, excluding density, to represent the VTI model. So we've got the vertical P and S wave velocities and anisotropy coefficients epsilon and delta. And we use multi-component data, so we use both the vertical and horizontal components of the data to perform our inversion. So the objective function is the very familiar L2 norm of the difference between the observed data D and model data U. So the objective is to minimize the objective function, and the gradient of the objective function is given by this second equation here. Del U del M is the Fresher derivative, and delta D is the difference between the observed and model data. So calculating the Fresher derivative is easy when we have a simple model. So like the one we had before, a layered model with a few model parameters. So we could numerically calculate the Fresher matrix explicitly and then perform the inversion. But this is not possible when we have a 2D model or a model that's varying in 2D. It becomes computationally extremely expensive. So what we do is we have to use the adjoint state method to compute the gradients. Now there have been a lot of papers, lots of authors have described or discussed the adjoint state method in order to obtain gradients. And most of them have been for the ones using the acoustic wave equation. There have been a few papers that describe the same procedure for elastic, using the elastic wave equation. And again, there are different methods of doing the same thing, but there's one in particular which we followed, and that's by setting up a problem as a constraint optimization problem. So out of the few papers that discuss about this specific problem, I think, and it's just my opinion, that the derivation we have in our appendix is one of the clearer ones. Should be easy to follow. So we set up at first the Lagrangian. So this is a constraint optimization problem. So we have a Lagrangian, capital lambda. It's defined. It's a sum of 2 terms. The first term is the objective function, which we want to minimize, and the second term is the elastic wave equation, the variable density elastic wave equation. We do not make any assumptions about the density being constant. This is the variable density elastic wave equation, because I've been asked this a number of times, so I want to make this clear at the outset. And U in the objective function has to follow this elastic wave equation, so it satisfies the elastic wave equation. Lambda I are the Lagrange multipliers. F is the source density, and in this case we are not looking to invert for the source location or the source parameters, but Oscar will later talk about inverting for source location and parameters. So the way to proceed from here is we modify, or we perturb the CIJKLs, the stiffnesses of the medium, which are unknowns in our case. We're just looking to invert for velocities, or so we perturb the CIJs, which results in a perturbation in the wave field, the model wave field. We also perturb the lambda i's, which are the Lagrange multipliers. These perturbations result in a perturbation in the Lagrangian, and then what we do is we find the relationship between the variation in the Lagrangian with respect to the variation in the Lagrange multipliers lambda I, the CIJKLs, and the model wave field UI. So setting the variations with respect to each of them to 0 gives us these three, gives us the state equation, which is the elastic wave equation, the adjoint state equation, which is also the elastic wave equation, and both are obviously for the variable density case. And finally, we get the gradient of the objective function, which is what we're looking for. So the gradient is this very innocuous looking expression. The model, it contains the model. It's basically the spatial derivatives, so we have the spatial derivatives of the forward wave field at the adjoint wave field, and we apply the imaging condition to this, and that's how we obtain the expression for the gradient with respect to the CIJs. So from here on, the previous reference that I gave you, Leo and Trompe, they go on to invert for an isotropic, an Earth model that's isotropic, and they use it for a geological scale problem, like a global seismology problem. But from here on, we're going to use the chain rule in order to obtain expressions for the model parameters of our choice for a VTI medium. And those model parameters are, again, as I mentioned before, the vertical P and S wave velocities and the P wave NMO and horizontal velocities. Choosing a model parameterization is up to us. We can choose. We can define the model in terms of the vertical P and S wave velocities and epsilon and delta, or the 4 velocities that I mentioned here, or we could include eta somewhere. So it's entirely up to us. We use these 4 parameters because we used the velocities to represent a model for the previous study, which consisted of a model with 4 or 5 layers, and it seemed to give us good results. So we have reason to believe that this should be appropriate, an appropriate model parameterization. And again, velocities are the ones that control travel times rather than CIJs straight away. So hence we use these model parameters. So now I'm going to go on to some very simple, some experiments for very simple models, transmission experiments where we have vertical arrays of sources and receivers as well as horizontal arrays of sources and receivers. So what you're trying to do is have a wave field that sample the model in a predominantly horizontal fashion and vertical manner. So the first experiment, we have these, there's a Gaussian anomaly in the center of the model. The anomaly is in epsilon. The background VP0, VS0, and delta are constant. So the yellow dots on the left represent sources. The vertical array, the magenta line on the right represents a line of receivers. So delta is fixed at 0.05 in the background, and if you notice, the change in epsilon is 0.04. So the difference between the maximum value of epsilon at the center of the anomaly and the background is 0.04. So we would hope that when we perform the inversion, the algorithm is able to update epsilon by 0.04. Now, as I said before, VP0, VS0, and VP0, epsilon, and delta are constant in the back. Okay, I'm sorry. So VP0 is constant in the background. Epsilon changes, as I showed you in the previous diagram. So when there's a change in epsilon, it would result in a change in V horizontal. So our model is parameterized in terms of the 4 velocities. So what we want is for the inversion algorithm to update V horizontal and not update anything else. So just updating V horizontal would result in an update in epsilon. So let's see what the algorithm does. So these results here in this slide and in the following slides are shown in such a manner that we're looking at the fractional change in velocities and the changes in epsilon and delta. So we see that the fractional change in velocity is very close to 0. The fractional in VP0 is close to 0. The fractional change in VS0 is very close to 0. The same for delta. And the only parameter that gets updated is epsilon. So ideally, we'd have liked the inversion to update the parameter epsilon by 0.04, but in this case, it just goes to 0.03. Again, we are dealing with very small values, so this is a reasonable result to expect. Next, what we do is epsilon and delta are constant in the background, VS0 is constant in the background, and now we change the VP0. So now the VP0 changes by 0.09 or 9%. So we want the inversion algorithm to update VP0. The fractional change should be 0.09 or 9%. Now, epsilon and delta are constant in the background. There's a change in VP0, which would result in a change in the other two model parameters we have, V horizontal and VNMO. So the inverse algorithm should update V horizontal, VNMO, and VP0, and they should be done proportionately so that there is no change in epsilon and delta. If, however, there is a change, if the change is not proportionate, then what's going to happen is it would result in a faulty update in epsilon and delta, and that would be bad for us. And that's exactly what happens. So for the given source receiver geometry, we see that the fractional update in VS0 is pretty small, it's close to 2%. The change in VP0 is roughly 5%. Now if you remember, we would have wanted an update by 9%, but this is just 5%. There is no significant change in delta, and that's because the change in VNMO is proportionate to the change in VP0. So both VP0 and VNMO are not updated to the right values, but since they're proportional, we result in almost close to zero change in delta. But there's a big problem in epsilon. So what's happening here is the change, the algorithm is updating V horizontal probably to the extent that it should. But since the change in VP0 is not complete, there's a positive change in epsilon. So what this says is, this experiment tells us is that if we have such a setup where we have got sources and receivers, vertical arrays of sources and receivers, we should be looking to update V horizontal and not VP0, because we cannot trust the result of that we get for the update for VP0 in such a setup. To test this, what we do is now we have got sources and receivers which are in horizontal arrays for the same model. So again, we expect the algorithm to update VP0 by 9%. Again, as I said before, there are trade-offs involved. So if VP0 is updated by the right amount but not V horizontal or VNMO, then it would result in faulty updates in epsilon and delta. And that's exactly what happens again. So here we see that the fractional change in VP0 is close to 9%. It's 0.08 and it's quite close to the right values. But because of the fact that V horizontal and VNMO are not updated accurately, we've got faulty updates in epsilon and delta. So here we've got large negative updates. And VS0 still doesn't get updated. So that seems to be sort of decoupled from these three model parameters. So yeah, from this experiment, it seems as if it seems that we should only be updating VP0 for such a setup, and we should not try to update V horizontal and VNMO or epsilon and delta. Finally, we have an anomaly in VS0, and we have so the fractional change is 0.19. So we expect a 19% update, or we expect the inverse algorithm to do an update by 19% for VS0. And the results seem pretty good. There are no changes in VP0, epsilon, and delta. VS0 is the only parameter that gets updated. And interestingly, or probably because of the fact that the shear wave velocity is exactly identical in VTI media along the vertical axis, the symmetry axis, and the isotropy plane, we get the same results even if we have vertical arrays of sources and receivers, which would mean the waves are traveling more in a horizontal manner. So we get pretty much the same result in both cases. So we perform FWI so the project is to the work we are intending to do is to perform elastic FWI for VTI media. We start off with transmission data, just for simple transmission experiments, and we invert for the 4 model parameters, which are velocities, the vertical P and S wave velocities, and the NMO and horizontal velocities. So we see there are major trade-offs between the 3 P wave velocities, VP0, VNMO, and V horizontal. And I'll talk about these trade-offs in my next talk, which is after lunch. And we see that we are able to constrain VS0, which is an added benefit because of including elasticity into the model. So the next step is to invert for a more realistic model, and of course to include reflection data. Then we would be taking into account amplitudes accurately. I'd like to thank discussions I've had with Gerhard and Tariq, and I'd also like to thank the members of A team and I team, especially Esteban, who's probably the master of Madagascar. Thank you.